The topic of today is how to write or how to author better flows. Everything that we will discuss today is going to be geared towards the AFL flows, but pretty much all of the tips, all of the problems, everything we discuss today can be directly translated to cloud slang. However, because cloud slang is more textual, a lot of the topics we are going to talk about here will seem more natural in cloud slang. So mostly because AFL is only visual, there is this disconnect. So the topic of the today presentation is going to be split up into several categories. So first we are going to talk about operational orchestration as a programming language. Basically note the similarities between traditional programming languages and the flows authored in operations orchestration. We are going to talk about how the variables are stored in memory, how they are passed in memory. Basically, it's where some of the problems occurs, where they come from. We are going to tackle on how to optimize our flows and then have a two-part demo. Since we are doing this parallel with the programming languages, the first part of the demo is going to be a short hello world example using the HTTP client operation and discussing how various versions and iterations of a flow can be improved. And the second part will be a more hands-on approach. It will be a more complicated example, and we will touch basically uh, pretty much all of the topics that we are going to talk about in the optimization part of the presentation within the two demos. Now, if you have any questions during the demo, feel free to ask directly. We are going to have some Q&A time after the demo, but uh, there is literally no problem if you have questions during the demo. So let's kick off with operations orchestrations as a programming language. Now, what defines a programming language? So basically a programming language is going to be composed of a set of default functions, statements, and procedures with which you can further build new flows, or new functions, new programs, and create new functionality. Now, when we're talking about OO, we have all of these tools at our disposal. We have the out-of-the-box content, which contains flows and operations. These will be our default functions. We have the capability to author new flows based on those default functions via Studio. And we also have the SDK with which we can create pretty much new operations. So from this point of view, we are quite alike when we're talking about the programming languages and all. Furthermore, when we're talking about this similarity of default functions which we then use, O is again not very different from the point of view that when you call in Java a print statement or any other statement, you will not have to look in the code and see everything that's been created in order to run that statement in one of your programs. You'll just have to uh, utilize the function with a set of parameters if needed. Similarly to OO, you when you run an operation, you don't actually care what's behind that operation. You don't need to know. You, you just need to know that if you drag a HTTP client step to the canvas, that HTTP client is going to make an HTTP client call based on the parameters you pass to it. So from this point of view, we are very similar to a programming language. Next, we have the loop support. So while in most programming languages, you have some structures which allow you to either iterate or pass or process or whatever number of elements through your code. You can do the same in operations orchestration. You have the list iterators, you have the counters, you have various conditional elements. Instead of having an all-encompassing if, you have the comparison operations. So compared to strings or compared to numbers, uh, check if something is null or not. So there is this parallel as well. And as I mentioned earlier, you can create new functions. So uh, basically, just like in programming languages, you can create new functions, new flows, or new operations. You can package them in content packs and deliver them either within your company or to the entire community, similar to how programming languages can distribute certain plugins which were basically created by third parties. So yeah, from this point of view, again, we are similar to a traditional programming language. The big difference and the big disconnect from this point of view is that instead of writing a lot of lines of code, we are just dragging operations or dragging content to a canvas and connecting the various steps of the flow visually. So yeah, because of this disconnect, it's easy to fall into some bad habits from traditional programming languages. Now, like some of the modern operating or programming languages, operations orchestration can be viewed as an object-oriented programming language. One of the best practices we always keep on saying when talking about the flows is create small atomic flows, create minimal functionality flows. Basically, uh, this is similar for object-oriented programming languages. You don't need to create huge million line programs in order to handle certain things. You create small programs and then bind them together in order to achieve your goal. So yeah, we have this view of creating small atomic reusable flows, just like object-oriented programming languages. Later on during this presentation, we will touch upon another point of view uh, why we are so similar to object-oriented programming languages. So now that we see this parallel between operation orchestration and programming languages, there comes a certain need both when authoring flows or when writing programs. And that need is optimization. Basically, just like when writing programs, you can write for the same functions several. Some say they can write 10 versions, other more, other less, doesn't matter. So you can write multiple versions of the same flow that does the same thing, but each version does it slightly differently, and each version can do it faster or slower. So basically, we are going to have to optimize similar to how regular programs also need to be optimized. Now, since we are talking about this optimization, the main problem that needs to be optimized is around variable management, which in turn will solve some other problems, such as, let's say, runtime or the footprint memory, RAM memory, or memory as in storage on the database. So basically, the variable management is the first place to start when thinking about optimization. Now, OO is built on top of Java, and as such, it's going to use Java's memory management tools. And one of the most important things that we need to remember from this is that in Java, any object that's held in memory, the size of that object is going to be both its own size and the sum of the children of that object. Now, because of this, it becomes crucial to have a good variable management. Uh, in the next slides, we are going to see how variables are passed within a flow. And keeping in mind this problem about the size of the object in memory, this is going to highlight exactly one of the problems. Now, whenever keeping variables in memory, these will eventually have to be uh, disposed of, destroyed, deleted, whatever you want to call it. Because we use Java in our application, the memory management is going to use the Java garbage collection. Now, for those who are not very familiar with Java, basically any objects that are referenced in Java, they are said to be live objects. Once they are no longer referenced, they are considered dead and are termed garbage. The process of finding and freeing or reclaiming the space used by these garbage or these not referenced objects is called the garbage collections. Now, Java prefers the garbage collection to occur on certain intervals. Uh, you can call it manually earlier or more frequently than normal, but if you call it too frequently, you are going to have issues both of performance while this garbage collection happens. Uh, the performance is severely reduced. Basically, if you call it too often, you're going to have a lot of dead cycles where data isn't being processed, it's just being analyzed to see if it can be deleted or not. And you risk crashing the JVM because it detects far too frequent garbage collections and suspects that a memory leak occurred. Now, when we're talking about memory from the OO context, uh, we need to keep in mind that besides the executions, there are a lot of other background tasks. So Central always has to manage the workers, to check on executions, to check various internal tasks. Are schedules supposed to run? Should I delete some data that is no longer used but it's stored in the database, and so on and so forth. Now, all these background processes also affect the JVM or the memory that's being used by OO. So writing, let's say, lean flows, flows that use the minimum amount of memory, is also going to help from this point of view. Now, as I said, we keep our variables for each execution in, let's call them, specialized containers or specialized memory areas we call contexts. So let's talk about this context from the point of view of an execution. So on one hand, we have this global context. Basically, the global context is created each time an execution starts. This is going to contain all the flow level inputs, all of the configuration items that are relevant for this execution. So basically, all of the system accounts that are detected that are going to be needed in the execution, all of the selection list, uh, system properties, domain terms to which you have access. So basically, if, for instance, you run as a user who doesn't have view configuration items, no configuration items will be loaded in memory. But if you have this permission in OO Central, all of the configuration items will be stored in this global context. Now, when you have flows in which all of the steps are operations, the global context and the next context, the local context, are going to be pretty much one and the same. But if you have multiple level executions, the local context and the global context will differ a bit. Now, uh, the local context also can also be called the flow context. This is going to be a child of the global context. It can communicate with the global context in certain conditions, but it will not have all of the variables from the global context. So in the local context, from the global context, again, all of the inputs that are required. So if we're talking a step that is a flow, you're going to inherit all of the inputs that were passed as flow inputs to that step, and all of the configuration items, and a couple of special variables. So at all points in flow execution, you're going to have access to the execution ID, the user ID, and the central URL. Now, these three variables are stored in the global context, but they are available in all of the contexts. You can also, through scriptlets, post such variables inside the global context, which will only be available for the duration of the execution. Now, uh, last context we are going to talk about is the step context. Now, the step context is actually, again, a child of the local context, and it's the context that's actually being used during a step execution. So you will have on this inside this context all of the inputs from the local context, all of the that so all of the inputs from the local context, specifically for the persistence in the database. However, only those that are relevant to the step are going to be persisted. All of the configuration items, the steps, results, and outputs. Now, why are outputs important? Outputs basically bridge the context. When creating a result on any step, there is a special, so there are two categories. There is the flow context, which means that from the step context, this new variable is going to be pushed to the local context or to the flow context. And then you have the flow output field. Now, the flow output field means that from the step context, this variable is going to be pushed up to the, let's say, outer edge, the border between the local context and its parent context. Why I'm saying the local context and its parent context is because the local context can be the child of another local context. So basically, if you have a subflow within a subflow, the parent of the bottommost local context is going to be another local context. It's not going to be a global. Once each of these contexts, so let's say the step context, once the step context is no longer in use, so the execution moved to the next step, the step context is going to be marked for deletion and is going to be deleted only when the next garbage collection event occurs. Now, because of that, if you're having flows which have a lot of high speed of execution steps, for instance, small processing or counters, steps that usually run in microseconds, between these garbage collection events, you're going to have a lot of contexts being marked for deletions. They're still in memory, but they weren't deleted yet. One thing to keep in mind when we're talking about these step contexts and local contexts, so each step on its own is like an island. It can see everything around it, but can only use the resources that are passed to it. So even if, let's say, on step one, I can see or on island one, I can see everything that's going on island two, it will not help me in any way because basically this is, I won't have access to those resources. Now, when talking about optimization, we need to talk about the problem. So the problem usually comes from large variables, as I mentioned. So where do we get these large variables? Well, we can have variable processes. So we have a list, then we compare it to another list, add more items, and so on. So through processing of data, we can compute these large variables, which will in turn impact us both on JVM memory and on storage in the database later on. We can, for instance, read large files, such as log files. Now, this can hurt us both on the side of overloading the memory by creating large variables, and also if we read a large enough file, we can overload the input buffers and basically run into problems of managing new steps during the execution. A very frequent problem is doing API or SQL query, and instead of having small results, getting very large results from these types of queries. Now, sometimes we need to process all of the data available that's going to be provided by either the API or SQL query. But that doesn't mean that we have to read all that data at once. And one of the errors that usually happen, especially to beginners, is having too big flows. Packing too much functionality single. There were cases where you would pack in a single flow the functionality to create property files for silent installation of a product, install the product silently, parse the logs, perform some basic configuration or verification tasks on that particular product, and then send an email that the installation was successful. Everything in one gigantic flow, and every bit of the flow would know things which it shouldn't. This leads also to bad variable manipulation or management. Steps which send email would basically know of how the decision where to install the product would happen. So all of these problems contribute to having flows that run a long time, flows that require a lot of memory to run, and if you require a lot of RAM memory, then storing them in the database, so the historical data, also has a huge footprint. So generally speaking, what can we do? As I said at the beginning of the presentation, smaller flows. Distill every bit of functionality to the very smallest bit you can. If you have, let's say, a flow that requires some form of timestamp manipulation, why not have all of the timestamp manipulation as a subflow, which then can be reused, instead of having each time that manipulation is required, all of those steps and variables in the main flow. Reduce the number of steps. Now, this is always a problem that's hard to deal with, because the more number of steps you have, the more contexts you keep in memory marked for deletion, and sometimes these are not necessarily required. Now, by reducing the number of steps, there is a risk or a trap that uh, you are going to work with larger variables. So it takes a bit of finesse to reduce the number of steps in such a way as to not overload the execution. Sometimes having more steps with less data is preferable than having a small number of steps with large context behind them. Use filters on results. Well, yeah, this seems pretty obvious. Well, sometimes some of the large variables are generated just in order to process them down to a smaller size. Now, through the use of filters, you can handle most of that processing on the step where you are retrieving the data. Tied to the previous option is using simple scriptlets. Sometimes if a decision-making step is required, a simple scriptlet could handle this instead of having to pass large data to the decision-making step. So basically, again, using scriptlets and filters together can both reduce the number of steps and reduce the size of variables in memory. Last but by no means least, clearing variables that are no longer required. Again, there may be situations where it cannot be helped. You have to pass a lot of data and have some more functionality than you would like. If certain variables are no longer relevant for that certain part of execution, and you know that they're not going to be needed later, this can be cleared either through operations or through short scriptlets. Either way, so yeah, clearing this data will also improve the quality of life. Now, speaking specifically on the topics of uh, the generators of large variables, when we're talking about API or SQL queries, most web applications provide some filtering capabilities on the API. For example, OO on the execution summary side provides a lot of filtering and even pagination options. So you could, in theory, get a smaller number of executions over a larger number of loops. Uh, Basically, this is a problem that if the web application knows that you can have large results for a specific API call, they are going to provide you with a filtering capability to limit the number of results. On SQL side, adding more conditions to the query in order to reduce its size, or providing smaller step. Utilize OS-specific tools to handle large files. Basically, operating systems will know if, for instance, where files are located or what they contain. So if we need this information, the operating system will be far better equipped to find this information for us than OO. Again, remove unused input from steps. What does this mean? Basically, you can have a lot of inputs that you're either not going to provide a value for, or they're going to use the default value all the time. Especially for the out of the box context, when you're dragging such operation or flow to canvas, uh, if you're not going to use them, why keep them in memory? Even if you remove them from the canvas, the operation itself is going to know these default values. So it's not necessary to pollute the environment to load up the contexts with extra unneeded variables if the content itself is going to know how to handle them. And lastly, when we're talking about processing, let's say, lists, you need to decide between two very opposing concepts. So you could either iterate through the list and process it through iteration, in which each member of the list is going to be uh, used sequentially, or you can parallelize them. Now, there can be merits on both sides, but there can also be pitfalls. So on a case-by-case basis, you need to take this decision, whether it's better to have an iterating and a lot of context marked for deletion, or have them parallel and have a lot of contexts in the memory at the same time. Sometimes it can be better to have them parallel, sometimes iterated. And now the demo part. So as I said, we are going to have two cases in the demo, a hello world and a more complex scenario. One second, please. Okay, so let's start with the hello world example. and then we'll move to the more complex scenario. So as I mentioned, we're going to take the HTTP client operation as an example this time because uh, this highlights the problem about inputs and whether you need them or not. So basically, the early versions of 10x and the previous version of operation orchestration 9x, when it came to variables, on all of the steps had this problem. So usually you assign the variable from a specific name or a key name. Otherwise, if that variable is blank, you can input a specific constant value or prompt or use a system account and then assign it to a variable of the same name. Now, what's the problem with this approach is if we run the flow, we are going to be generating on each step a lot of inputs and variables which also have to be stored in memory. So if we look at the HTTP client step, we are going to see all of the inputs. So all of the inputs that the step had, we are going to see also the step context in Studio. So let's close a bit the step inputs. And again, on the step context, we have all of the inputs and the results. The global context with the basically the variables which I mentioned that are always available, and the configuration items. In this case, we have only selection lists. Now, where this becomes a problem is on the next step. Okay, so on the step inputs, again, here we have only 3 steps. We have the operation, value 1, and value 2. However, because of that broken behavior, we have all of the inputs from the previous step on top of our inputs and the transition. Now, from a memory point of view, this is very inefficient. I'm just comparing two numbers. Why do I need to know a URL, a connection timeout, a user, a password? There's basically no need. So in 10x, what we did is that by default now, we're not assigning anything on the steps when we're dragging them to the canvas. So they're not assigned from any value and they're not assigning to any value. Granted, you could assign it from manually, but you have to take that decision yourself. Now, with 10x, so if we run the 10x model, again, we'll see on the HTTP client step, all of the inputs from the HTTP client and its results. But on the step context, because in this case, we're not creating new variables, we'll just see the two results of the HTTP client step and the global context and selection lists. And again, similarly on the comparison step, we are going to see the same result. But yeah, this is better than 9x, but this is not exactly better. It can be improved. So let's take a look at an improvement. As you saw on the previous execution, I have a lot of step inputs for the execution for the HTTP client. In total, there are 20 something inputs on that step, but I'm just getting I'm using the get method to get the execution summary of a central. Surely I don't need query parameters and form parameters and multi-part bodies and all that, because quite literally, I'm not using it. In my case, since this is a demo environment, all I'm using is the URL, the authentication type, username, password, the security aspects of certificate management and hostname verifier, and the method. I'm using it, so I don't need to pass anything other to the execution. So I've deleted from the step all of the extra inputs which either I'm never going to use or the defaults will be fine with me. Okay, so now we're going to run this, let's say, improved flow, and instantly we are going to see that on the HTTP client step, I have considerably less variables in memory. So on one hand, I'm using less memory to execute this step from the point of view of storing variables. And I'm using also less memory from the point of view of creating variables, checking if they exist or not, and so on. So basically, already I'm doing better. But if I look at the comparison step, I'm still bothered by the fact that, okay, I have this huge variable of executions uh, still on that step. And why should that step actually know of these executions? I mean, all it's doing is comparing two numerical values. It makes no sense for me to pass this huge variable. So let's improve it further. Now, the second improvement, so as you can see, is, well, I no longer have the step to check whether my call was successful or not. Now, when it comes to HTTP client, as most of you know, the HTTP client operation will perform the HTTP client call, and if it's successful, which means I perform the call and receive a response, it's going to go to success. Now, it doesn't care what the response is. The response could be 200, okay, everything is all right. It can be 401, unauthorized. It can be 500. It can be anything, but it got a response, so it's successful. So by using a short scriptlet, I can perform the verification which normally I would need yet another step to do on the same step. So if we run this new and improved version, yeah, so I have all of the data I need. I have only one step, and everything that's going on in this step is relevant. So all of the memories, all of the variable that I have in memory are relevant for this step. And just so we know that I'm not cheating, I'm going to edit this flow and try to get it to fail. So yeah, the script works. In this case, I got uh, so the status code is 404 not found. It couldn't find the page I was looking for. And yeah, the script correctly failed the HTTP client request. Basically, this means that this is working. So uh, what now? Well, now the next thing to do is, when we're talking about HTTP client, as I mentioned, I'm getting 100 executions per call. Maybe if I were to say do only 20 executions and run it 5 times, yeah, I would have more steps, but overall I would have smaller variables to process and to check. So in that case, I would have less memory impact. If there are any questions on the Hello World example, if not, let's pass to the next example. Okay, so for the next example, let's take a task that is more close to a real life scenario. So what happened is that for a specific reason, we need to examine the OO workspace of Studio and check to see if there are multiple flows either with the same UUID or if there are flows duplicated. And because if we encounter such a scenario, we need to identify the location of these flows, we need to store this information in a simple CSV file. Now, I've created for the purpose of this demonstration 2 flows which pretty much handle the same task. So there is the first flow. Basically, this one has only 2 steps, which are flows, both. And if we drill down into them, okay, we see the first one gets the contents of the repo, then iterates, does some verification, and exports the list of flows, while the second one utilizes that list, iterates it again, and writes it to a file. But if we look specifically at the top level, we just see 2 flows with 1 input each. Actually, okay. Now let's look at the second flow. So the second flow already looks much more complicated because it has 3, 6, 7 steps, and each step has has 4 inputs. So the first one has 4, then 1, then it switches to 1. Okay, and if we peek into these flows, we'll see that it does some file system checks and then runs a script. So right now, we cannot say anything about these flows. We don't know which is best. On one hand, we have a flow with 7 subflows, and on the other hand, we have a flow with only 2. So the deciding factor this time is going to be what happens when we run these flows in Central. So let's run the first flow. So if we look, this is going to be the flow with only 2 steps. Okay. So it starts running, and if we look at the, okay, it's still inside the first subflow. Now let's wait for a couple of seconds, let it finish. So why I'm saying that we need to let it finish, this will run something like 1 minute, something like that, because we need to further analyze this flow and see what happened inside it. Okay, so it completed in 53 seconds. It has a lot of steps. Okay, if we look, okay, so it generated our CSV with all of the flows with their specific UID. We have 102 flows. And if we look at the central execution, so for the 102 flows, it took 4,507 steps to execute everything. So 4,507 steps with potentially large contexts attached to them. Okay, let's run the second flow. So this one has 7 steps. Okay, it started running. Okay, oh wait, by the time I finished watching, so this one completed in only 3 seconds. Already much faster than the other flow. So, okay, so the random. And if we look, the CSV also has the 102 flows with their UUIDs, but this one completed much faster. So it only took 36 steps and completed in 3 seconds as opposed to nearly 1 minute. Now, why is that? Well, it's quite easy. While the first flow has a small apparent number of steps, in the background it tries to reinvent the wheel. So what do I have to do? Well, I have to get the file locations, decide if it's a file or a folder, then if it's a folder, put all its context back into the original list which I'm iterating, and continue. Now, if it's a file, check if it's an XML. If it's a valid XML, put it in the XML list, and so on. So at the end of at least this flow, we are guaranteed to have 2 huge lists. One, the list of all the content in the file path that I gave it, and the second list, the XML list. Then I take the XML list and further process it. If it's an XML, read from the file, get its UUID, and write it to the CSV, which it's very time consuming, very bad from a memory perspective, because all of the data that somebody already knows, I have to keep it in host memory. On the second approach, basically what am I doing? So I'm asking the operating system, okay, tell me on the specific repo path if I have flows, valid XMLs, and write all that information into a temporary text file. And from that point on, all I need to know is the location of that temporary file and we're good to go. Then operating system, read that temporary file and format the information so as it's in a format I need. Split the temporary file into separate lines, eliminate any possible false positive, uh, clear any other data that I don't need except for the UID, remove empty lines, and finally save it as a CSV. So the operating system pretty much knew most, if not all, of the information I was requiring from it. And it was better from the OO perspective to ask the operating system what about that information instead of me having to manually go through all of that data, which from the OO perspective, yeah, I can obtain it, I can do it, but it has little meaning. So as such, we are able to reduce in this scenario both the number of steps, which means less data being written into the database, uh, less memory used for the execution overall, reduce the size of variables used in memory. I'm just utilizing username, password, and a file location to the local file system. So overall, this is the level of improvement you can do if you follow those tips I mentioned in the presentation.